Yours.
Okay, we are well below quorum. So what I'll do is I will give you the correlations that I promised to give you yesterday so that everybody can use those graphs, which are analogous to the free settling graphs I gave you, but now valid for packed beds. Okay. So if you remember, I derived from first principles the drag force per unit S, capital S, which was meter cube per meter squared per meter cubed. Okay. And I did this by the force method that we have been using. And also earlier last week, I showed that it could be done phenomenologically without knowing much about forces. Okay. So what we required to use the correlation for packed beds was a graph which plotted R prime, which was the component of the drag force that was operative, okay, per unit area of the particle surface, divided by we divided that through by rho u1 squared, where u1 was the average velocity through the interstices of the packed bed. That was the y-axis. And the x-axis was the modified Reynolds number, which was all depending on the properties of the packed bed and the fluid, right? So it included the void fraction E, the specific solid surface capital S in meter squared per meter cubed per unit volume. It included the rho density of the fluid and the viscosity of the fluid, etc. Right? That was the modified RE. That was the x-axis. And I also derived for you a relationship between R prime and delta P, which is equation 9 on your screen. Okay, so if I knew R prime, I can figure out what is the delta P across that bed. And of course, I need to know what the velocity is. And the velocity on the x-axis is always taken as small u, which is the superficial velocity. Okay, while the velocity in the on the y-axis is u1, which is u divided by porosity epsilon. Okay, so don't mix the two things up. Okay, so there are two different velocities, but knowing the void fraction, you can always interconvert from the superficial velocity far away, assuming the bed is empty, to the velocity u1, which is inside the bed. Okay, so R prime is related to delta P, and I derived you the equation also in terms of modified Reynolds number, and we showed that it's inversely proportional to RE, and the constant for low Reynolds number is 5, which is the value of K in this equation. All right. So, but as I said, the curve is very general, not just for RE less than 1, but it also has same three regions like we have been repeatedly presenting earlier. And if you remember, there was the intermediate and the turbulent flow region. And gradually the slope of this R prime upon rho u1 squared versus modified Reynolds number starts decreasing from 1 in the low RE less than 1 regime to a value of close to 0 for turbulent flow. And the intermediate region is the slope changes from 1 to 1/4 approximately, and then the graph stabilizes. So I wanted to give you, very similar to the free settling graph, I wanted to give you the graph that you can use, which is there in the slide displayed. So you have r prime upon rho u prime squared on the y-axis. Okay, r prime upon rho u prime squared on the y-axis, and you have u into rho, where u is the superficial velocity, rho is the fluid density, and then capital S in the denominator, specific surface area per unit volume of the solids, then it's mu, which is the liquid viscosity, times 1 minus E, where E is the packing void fraction. Okay, and this is a log-log plot. So it goes from less than 0.1, so 0.01 to little over 1,000. And once you go to the right extremity, you can say that the slope has become 0. And the slope in the intermediate region goes from 1 at RE less than 1 all the way to 0. And in the points where the data is in the intermediate region, it's between 1 to 1/4. And then beyond 1,000, you can approximate it by what we call the Newtonian regime in earlier discussion for settling. But it's called the Blake-Plummer limit in our case for the packed bed, because Blake and Plummer derived the turbulent flow limit with 0 slope. So if you don't want to use this correlation, you can also use the correlation given here, where again you have, but now you see they have defined, you see different people define the modified Reynolds number differently. So here this is actually the Reynolds number itself. All right, that's the x-axis, and then there's the modified friction factor. It also has similar terms like we had E cubed 1 minus, and in the numerator 1 minus E in the denominator, that's given on the y-axis. Okay, and again you have the Carman Kozeny limit. That's what I defined you with the slope -1 on log coordinates. Okay, and then here this graph gives you the Carman Kozeny slope of -1 for RE less than 1, and it also gives you the Blake-Plummer limit in turbulent flow beyond RE greater than 1,000, and in between you have the intermediate flow, just as we had earlier, where the slope gradually changes between -1 and 0. Okay, so you can use the treatment that I did exactly, which is the previous correlation. Or if you don't want to use it and you don't want to use R prime, but you want to use friction factor, which is the, sorry, there's a plane, which is the Bird-Stewart-Lightfoot approach, you can use the other second graph. And or anyway, what I feel is once R prime is known, you can calculate the delta P as I showed you by the general equation. So you have the whole correlations for a whole several decades of Reynolds number or modified Reynolds number in the first graph, and that goes from 0.01 to at least 1,000. Okay, and as I said, all the data fall on a single curve. Okay, now there are those. So this part is, I think, unless some question is raised, I am fine with it. Okay, if there's any question, you can ask me. But otherwise, there's so many embellishments of this that can be done, and perhaps some we can take up after minor. For instance, if you see, this was suppose you had accelerating flow. I mean, and the particles will start moving about, as would happen in a fluidized bed. Then what form will this curve that I showed you as a function of Reynolds number in how will that change? Will it go up? Will it go down? Will it superimpose on the curve given? See, don't forget that whatever we did last time, well, last time meaning for settling, that is only valid for a terminal condition velocity. It's not valid for accelerating particles. Suppose now, even in that free settling case, I said that, well, particles are accelerating, then what will happen to that curve? Similarly, in packed beds, what will happen? Suppose the bed is no longer perfectly packed, but above an incipient or a critical flow velocity, the bed starts expanding. Then what will happen to this curve? So a lot of these things have to be reasoned out based on the forces approach. And if you want, we can look at some situations after after the minor. And for instance, if the bed expands, so there will be there's a pressure drop due to upward flow of fluid through the granular bed. But then the weight of the packing is also there, and somehow, at least at the incipient condition, just when the bed starts expanding, we should be able to apply the same force balance, you see. However, once that incipient condition is not satisfied, then the porosity of the bed starts increasing beyond what we call E. And so then the bed is called fluidized, because the individual particles sort of start moving, and the bed is no more packed, particles are no more stationary. And this is a very important application in so many chemical engineering industries. All catalysts, all heterogeneous catalysts, including for environmental applications, are built, are synthesized in fluidized beds, such as all these catalytic converters in cars and Euro, this 6 norm and 5 norm. And so we need, all of these are manufactured by fluidized bed technology. Okay, and now, however, you can write a force balance up to the incipient condition, and then what will happen beyond that? All these things can be derived, and I shall cover some of these things after the minor. But right now, we are interested in the bed staying stationary, particles not moving about, bed being packed, and we want to find velocities in the bed, superficial velocities. We want to find pressure drops, and I have given you the equations and also the curve, which you can consult. And don't forget, the first curve is also in log coordinates. So there's only every, so 0.01, 0.1, 1, 10, 100. So you have to interpolate logarithmically in between those squares, okay? The smaller sub-squares are not given. So it's also distributed between these decades. It's distributed logarithmically, okay, not linearly. So please don't forget that. So this is what we wanted to cover up till minor, and I'm fine with it. Now, this has 30%, right? So there was also another 30% for your group. You were to make a group, So can you please work on that, because there is some time left, and you can and then communicate to Sarthak Chahal, your group members, at least you start on that, because that has another 30%. And I am not yet aware of if you guys have started on all of these things. Okay, so the graphs are here. Both the graphs, the force-based approach that is on screen now, with r prime upon rho u1 squared, or what I also call rho u prime squared, where u prime, u1 all refer to the average velocity inside the interstices of the packed bed versus modified Reynolds number, or also the friction factor approach, which is also there. And you can use all of those things. And I want to say that these approaches can be extended to a number of other even more interesting and industrially important situations. And maybe we can do some of those things in the after your minor is over. What I want you to do is at least make the groups of 6 or 5 or 6 people, up to 6 people, so that you can start on that. I'm not sure if anybody has done, because neither Sarthak has given me any group mates nor a topic, what your topics are. Please start thinking, because 30% is, and if you just crash it in a few days, it's not going to be great fun. All right, so I think if you have no questions, then we are done. An exam on Monday, 3 p.m. and some time will be given for you to read the question, and then automatically the counter will start and you will submit it before the time limit of whatever, 45 minutes, 40 minutes, whatever that will be given to you. Okay, any questions? All right, then please look at these correlations and make sure you can use them. I can't anticipate any, unless you ask me, it's very hard for me to anticipate any problems in what we have done or up till now. All right, then good luck to you. Please use the time also to worry about the group members, and then start, and after minor you must zone in on a topic. Okay, thank you.